Hello everyone, so today we're going to go over section 9.3 part B, solving exponential equations. So if we look at example number 1, we are given this formula for the tripling of bacteria over an X number of days. So in this case, if we're looking for the day on which there are 243 bacteria, n is going to be equal to 243, and we're going to solve for x. So what we can do is to rewrite both sides so that they both have the base of 3. 243 is 3 to the 5th power. So 3 to the 5th power is going to be equal to 3 to the x over 6 power. In other words, 5 is equal to x over 6. So therefore, x is equal to 30 days. Okay. Example number 2, a painting doubles in value every 8 years, is currently worth $1,000, so we're looking for the year on which it will be worth $32,000. Okay. So on the left-hand side, we have the value, the present value P of 32,000. On the right-hand side, we have the initial value of 1,000 multiplied by 2 to indicate that the value doubles, and x over 8. So this x over 8 exponent indicates to us that the value doubles every 8 years. Simply put, then, we can divide both sides by 1,000 first. Let's go ahead and do that. So the left-hand side simplifies to 32, and the right-hand side of the equation will now be 2 to the x over 8 power. We can then rewrite 32 as power of 2, so this will be 2 to the 5th power, and that's equals to x over 8. So simply then we have 5 on the left-hand side, x over 8 on the right-hand side, and finally x is equal to 40 years. Okay. So those two questions, examples 1 and 2, are about exponential growth. Let's look at a question with exponential decay. It involves a radioactive isotope with a mass of 512 grams and a half-life of 3 minutes. So in this case, we have the 512. Just like in the previous question with the 1,000, this is the initial value. So in the previous question, it was about the initial value of the painting. Here is the initial mass of the isotope. The 1/2, of course, is the base. Since we're looking at half-life here, the base is going to be 1/2. In the previous question, we're looking at how long it takes the painting to double in value, so the base was 2. And finally, this 3 here is, of course, in minutes, and it indicates to us the period until the mass is halved. So we're looking for how long it takes for the mass to be reduced to 1 gram. So we can set it up as 1 is equal to 512, and then 1/2 to the m over 3 power. We can divide both sides by 512. So on the left-hand side, we have 1 over 512. Sorry about that. And on the right-hand side, we have 1/2 to the m over 3. We can then rewrite 1 over 512 as a power of 1/2. So we get on the left-hand side 1/2 to the 9th power. And on the right-hand side, we have 1/2 to the m over 3. So that tells us that 9 is equal to m over 3. So the time it takes is 9 times 3, or 27 minutes. Okay. So in these 3 questions, we have examined half-life, where the base is 1/2, generally about radioactive substances decay. We have the doubling time, so that was the first one, the half-life here. We have the doubling time, the time it takes for an exponential function to double in value. So that's doubling time. The base is 2, and the time is the d here. The half-life is the h. And finally, tripling time, very similar to doubling time, except for the base is, of course, 3 instead of 2. Okay. So another type of exponential growth question we can look at instead of doubling time or tripling time is if we're given a percentage increase. So let's look at that as well. In example 4. So a student council of a school notices that their membership is growing by 5% per year. The membership is currently 400 students. So if we were to write an exponential function to model the size of the student council, then the number of students, we'll just call that A, is going to be equal to 400, that is the initial value, multiplied by 1.05, and then to the t power. So the 400 is, again, the initial value. The 1.05 indicates a 5% increase per year. Right, so 1 to indicate the 100% that is retained from before, and the 0.05 to indicate the 5% increase, so added together is 1.05. And finally, the t, the variable, is of course time, and it's going to be in years. Okay, so if we were to figure out how many years it would take until the student council reaches 500 members, the way that we're going to do this is by looking at the number of students year to year. So in the first year, this will be simply 400 times 1.05 to the first power, so that's 420 students. The year after that, that is going to be 400 times 1.05 squared, or we can also think of it as 400 times 1.05 times another 1.05, because that's how we can have successive 5% increases in the 2 years. So that will give us 441 students in the student council. The year after that, again, 400 and then 1.05 cubed. And here we're going to start rounding to the nearest student. So that would be 463. And from there, same thing again, 400 and then 1.05 to the fourth power. Sorry about that. And that will give us 486, which is very close to 500, but not quite. So in the next year, we once again have 400 times 1.05 to the fifth power, and that will take us finally over 500, and we end up with 511 students. So it will take 5 years. Now, this is obviously not the only way to do the question. Of course, we can attempt to do the question algebraically, and what we end up with is 500 is equal to 400 times 1.05 to the t power. And then we can divide both sides by 400, so we get 1.25 is equal to 1.05 to the t power. And of course, the problem that we run into is we don't have a good way of solving for t as of right now. That will come in the next unit. All right, so example 5. An investment of $4,500 is growing by 15% per year. So if we were to write an exponential function for that, very similar to the previous example, we have A, the amount, is equal to the initial value of $4,500. And then since it's a 15% growth rate, so that will be 1.15 to the t power. So it's going to show the first of the computations. It says, how long does it take to double in value? So after the first year, we're going to take 4,500 and multiply by 1.15 to the first power. That will give us 5175. And then the next year, so on the calculator, we can simply multiply by the value by 1.15 again to get the next value. That will be 5951.25. All these will be rounded to the nearest dollar and cents. So 6,843.94. And then from there, $7,870.53 in the 4th year. And finally, on the 5th year, we finally reached 9,000, which of course is double the value from initially what we had. So $9,051.11. So that is to say, on the 5th year, the money doubles. Okay, so we are going to rewrite the equation from part A as an exponential function if base 2. So we have, once again, A is equal to the initial value of $4,500. We want to write the exponential function with a base of 2, so base 2 right here. And we know that the doubling time is close to 5 years, so we're going to have n over 5, or actually t over 5, because this is in time, of course. Now, knowing our exponent laws, we can rearrange this slightly. So we have $4,500, and then 2 to the 1 over 5 power to the t power. And if we were to evaluate on a calculator what 2 to the 1 over 5 is, then we have $4,500, and this works out to be approximately 1.149. Again, that is approximate. So the idea is that the value of 1.149 is very close to 1.15. So this doubling time of 5 years is a very good approximation, as that's what we found in part B. So if we are given the rate of growth, R, we can write our exponential growth equation this way. So P, as in the present value, is equal to the initial value P naught times 1 plus R to the n power. For the other questions, if we're given the doubling time instead, then our exponential growth equation will be written in this A amount is equal to the initial amount and then 2 to the n over d. Okay, so both of these in general will be about exponential growth. As in the amount is increasing exponentially. So be that amount be value or number of bacteria or number of people in student council, anything like that. All right, so let's look at exponential decay next. Example 6 says here, for every meter below the surface of water, the intensity of the color red of the light is reduced by 35%. So go ahead and write an exponential function for that. So the percent of the surface light is equal to, of course, it starts at 100% on the surface, and it's going to decrease by 35%. So 1 minus 0.35 to the n number of, to the, I guess we're using the variable d here. All right, so once we subtract here, this is 100 times 0.65 to the d power. And that is to say that for every meter under the water, only 65% of the color red is retained. So we're looking for the number of meters until 18% of the color red remains. So let's say n equals 1. So we have p, is equal to 100 and then 0.65 to the first power, which of course is just 65% of the light. And then we have n equals 2. So p is equal to 100 and then 0.65 squared. And that will be 42.25%. It's very similar to the questions on the previous page, but that we did using table. Same thing, when n is equal to 3, then p is equal to approximately 27.46%. And then finally, when n equals 4, or d equals 4, sorry about that. I don't know why I keep on changing the variable. It should be d here. So when the depth is 4, then that's when we get p is approximately equal to 17.85%. And that's close to 18%. So the answer to our question is, well, 4 meters. Okay. Next one, according to the manual, the battery in a cell phone loses 15% of its remaining charge each day until it completely drains out. So very similar to the previous question, the remaining charge is equal to 100%, and then it's a 15% decrease, so 1 minus 0.15 to the number of days. So let's just call that n. So that will be c is equal to 100 and then 0.85 to the n power. Okay. Determine the number of days until only 50% charge remains. So very similar to the previous example, we can let n equals 1. Then c is going to be equal to 85%. N equals 2. Then c is going to be 72.25%. Right, we can just repeatedly multiply by 0.85 as we go. So we can take 72.25 and then multiply that by 0.85. That will give us approximately 61.41%. So we're getting very close to 50%. So when n equals 4, we get c is approximately 52.20%. And one more year, we will have the 5th year. And that's when the charge is below 50%. It will be 44.37%. So the closest number of days would be 4 days. So just as we were able to rewrite an exponential growth equation using doubling time, we can also rewrite exponential decay equation using half-life. So it says here to do just that. So C is equal to 100%, and then 1/2. And we know that it takes 4 days to get half the battery charge, so this would be n over 4. So just as before, we can look at it as 100, and then 1/2 to the 1/4 power to the n. And if we were to evaluate 1/2 to the 1 over 4th power, we should get some number that's very close to 0.85. And we kind of do. We get 0.84. Okay, so not as good as approximation as last time, but still pretty good. So this is close to 100 and then 0.85 to the n power, which is what we had at the beginning. Okay, so once again, the idea here is if we're given the rate of decay, we can write our exponential decay equation this way. If we're given the half-life in terms of time d, we can write our exponential decay equation this way. Okay, so one more small topic involving exponential equations. And that is compound interest. So the principal of $A0 is invested in an annual interest rate of I, and then with n compounding periods per year. So typical compounding periods would be annually, so that's once a year, semi-annually, so twice a year, quarterly, so 4 times a year, monthly, so that's 12 times a year, weekly, 52 times a year, and finally daily, that will be 365 days in the year. So the amount $A after t years is given by this equation right here. So let's put that into our example. It says here, principal of $1,000 is invested at 6% in annual interest rate compounded monthly. So we're looking for the amount A, and that's going to be equal to the initial amount of $1,000 in this case. And then we have 1 plus the interest rate is 0.066%, divided by 12, because that's 12 compounding periods per year. And then to the power of 12t. Okay, so in this case, 0.06 divided by 12 is 0.005. So we can simplify this a little bit. So A is equal to 1,000, and then 1.005 to the 12t power. Okay, determine the value of the investment after 4 years. So we can simply let t equals to 4. $1.005, and then 12 times 4. So we will take 1.005 and raise it to the 48th power and then multiply it by 1,000, which gives us $1,270.49. Again, this is rounded to the nearest cent. So the next piece, to the nearest whole year, when would the amount be $1,400? So this involves solving for t, which we don't have a good way of doing right now. So again, we have to kind of guess and test a little bit, but we know it's going to take more than 4 years, because after 4 years, the amount is only $1,270. So let's see what happens on the 5th year. So again, 1000 times 1.005 to the 12 times 5 power. That gets us to $1,348.85, which is not quite 1,400. So let's see if the next year will take us over the amount needed. So this will be 12 times 6. And once everything is done, we get $1,432.04. So all in all, it's going to take 6 years to get to $1,400. Okay. Again, in order to solve for t directly without using this trial and error method, it requires logarithms, which is the topic of the next unit. But that is it for today. And once again, thank you for listening.